September 15, 1940, and the acrid smell of burning aviation fuel filled the underground laboratory beneath the Royal Aircraft Establishment at Farnborough. Chemical engineer Thomas Whitmore wiped sweat from his brow as another test batch failed, the thick black smoke billowing from the small combustion chamber telling the same story as the previous 47 attempts. His hands trembled not from fear, but from exhaustion and the crushing weight of knowing that every hour of delay meant more Spitfires falling from British skies. The official fuel specifications from the Air Ministry lay crumpled in the corner, regulations he was about to violate in the most spectacular way imaginable. Above ground, the Battle of Britain raged with unprecedented fury, and the Luftwaffe's superior fuel technology was giving German fighters a deadly advantage in altitude and speed that British pilots paid for with their lives. Whitmore stared at the forbidden mixture of chemicals on his laboratory bench, compounds that every textbook and military manual declared too volatile, too dangerous, too experimental for combat use. His superiors had explicitly ordered him to abandon this line of research 3 weeks earlier, calling it reckless chemistry that would kill more pilots than it would save. But the mathematics were undeniable. British aircraft needed more power, and conventional fuel simply couldn't deliver the octane rating required to match German performance at 30,000 feet. As air raid sirens wailed overhead and the building shook from distant explosions, Whitmore made the decision that would either court-martial him or revolutionize aerial warfare. He reached for the flask of his experimental fuel additive, knowing that one man's defiance of direct orders might be all that stood between Britain and invasion. No one in the Royal Air Force knew that one chemist's rebellion that evening would rewrite the physics of flight and ultimately power the very machines that would carry the war to Hitler's doorstep. Thomas Robert Whitmore had never intended to become the man who would challenge the entire British fuel establishment. Born in the coal-blackened town of Sheffield in 1908, he was the third son of a steel worker who barely earned enough to keep food on the family table. His mother, Margaret, worked 16-hour days in a textile mill, her fingers permanently stained with dye, but she possessed an unwavering belief that education could lift her children from the industrial poverty that had claimed generations of Whitmores before them. Young Thomas showed an early fascination with chemistry, conducting crude experiments in the family's cramped cellar using household substances and salvaged laboratory equipment from the local grammar school. His teachers recognized exceptional talent beneath the rough Sheffield accent and patched clothing, and by age 16, he had earned a scholarship to study chemical engineering at Cambridge University. The transition from working-class Sheffield to the prestigious halls of Cambridge proved jarring, with classmates who spoke in polished accents and possessed family connections that Thomas could never hope to match. He compensated for social disadvantage through relentless study and an intuitive understanding of molecular chemistry that impressed even his most demanding professors. During his final year at university, he wrote a thesis on fuel additives that challenged conventional wisdom about octane enhancement, proposing theoretical compounds that could dramatically increase engine performance. His academic advisors dismissed the work as too speculative, too dangerous for practical application, but Thomas graduated with highest honors in 1931 and immediately sought employment in Britain's emerging aviation industry. The Royal Aircraft Establishment at Farnborough offered him a junior position in their fuel research division, where his job involved testing existing formulations rather than developing new ones. His colleagues found him brilliant but stubborn, a man who questioned established procedures and proposed modifications that made senior engineers uncomfortable. He earned respect through meticulous work and an uncanny ability to diagnose fuel-related engine failures that baffled other specialists. By 1938, he had been promoted to senior chemical engineer, but his superiors remained skeptical of his unconventional theories about high-octane fuel development. He had no idea that soon those controversial theories would be all that stood between the Royal Air Force and complete defeat. The broader context of Britain's fuel crisis in 1940 revealed a technological gap that threatened the nation's very survival. When war erupted in September of 1939, the Royal Air Force discovered that German aircraft consistently outperformed British fighters at high altitude, where combat increasingly took place. The Luftwaffe possessed access to synthetic fuel technology developed by German chemical companies, producing aviation gasoline with octane ratings of 100 or higher, compared to Britain's standard 87 octane fuel. This seemingly small numerical difference translated into devastating battlefield advantages. German fighters could climb faster, fly higher, and maintain superior speed during critical combat maneuvers. British pilots found themselves perpetually fighting uphill battles, literally and figuratively, as Messerschmitt fighters operated with impunity at altitudes where Spitfires and Hurricanes struggled to maintain engine performance. The mathematics of aerial combat became brutally simple. Higher octane fuel meant more powerful engines. More powerful engines meant tactical superiority, and tactical superiority meant dead British pilots. Intelligence reports confirmed that Germany had invested heavily in fuel technology throughout the 1930s, developing synthetic production methods that freed them from dependence on imported petroleum while simultaneously creating superior combat fuels. Britain, by contrast, remained locked into conventional refining techniques and conservative fuel specifications that prioritized safety and cost over performance. The Air Ministry's procurement policies favored established suppliers who produced reliable but inferior fuel, while experimental research received minimal funding and faced bureaucratic resistance at every level. By summer of 1940, as the Battle of Britain intensified, RAF fighter squadrons were losing experienced pilots at unsustainable rates, with many casualties directly attributable to German altitude and speed advantages. Squadron leaders filed increasingly desperate reports describing combat situations where British aircraft simply could not match enemy performance, regardless of pilot skill or tactical innovation. The fuel gap had become a matter of national survival, but changing established procurement systems required overcoming decades of institutional inertia and risk-averse thinking. Winston Churchill himself had begun asking pointed questions about British technological capabilities, demanding explanations for persistent performance deficits that cost lives and threatened invasion. The pressure for solutions intensified daily, but solutions required someone willing to risk career and reputation by challenging the entire system. Throughout August and September of 1940, Thomas Whitmore watched the Battle of Britain unfold with growing frustration and determination to solve the fuel performance crisis. His official duties involved testing batches of standard aviation gasoline for quality control, ensuring that fuel met existing specifications rather than developing improved formulations. However, his laboratory access and chemical expertise positioned him uniquely to understand exactly why British aircraft continued losing critical engagements despite superior pilot training and aircraft design. He began conducting unauthorized experiments during evening hours using laboratory equipment and chemical supplies without official permission to explore fuel enhancement possibilities. His theoretical work from Cambridge had identified specific chemical compounds that could dramatically increase octane ratings. But implementing those theories required violating established safety protocols and procurement regulations. The Air Ministry had explicitly prohibited experimental fuel development by individual researchers, requiring all such work to proceed through official channels with proper oversight and approval. Whitmore submitted multiple formal proposals for high-octane fuel research, but each submission disappeared into bureaucratic committees that prioritized established procedures over urgent battlefield needs. Meanwhile, combat reports continued documenting tactical defeats that cost lives and aircraft. with pilot testimonies describing repeated situations where German fighters simply climbed beyond British pursuit capabilities. His colleagues in the Fuel Research Division acknowledged the performance gap, but insisted that solutions must come through official channels rather than unauthorized individual initiatives. The weight of institutional resistance might have deterred a less determined person, but Whitmore possessed both technical confidence and moral conviction that drove him beyond conventional boundaries. He began stockpiling chemical components needed for his experimental fuel additive, acquiring materials through creative interpretations of existing supply authorizations and personal relationships with laboratory suppliers. Each evening brought new calculations, new mixture ratios, new attempts to create the high-octane fuel that could level the aerial battlefield. His work consumed increasing amounts of time and energy, but every failed experiment brought him closer to the breakthrough that would vindicate his theories and potentially save countless lives. The pressure intensified when squadron leader James Morrison, a family friend from Sheffield who flew Spitfires with 609 Squadron, visited Farnborough and described in vivid detail how fuel limitations forced British pilots into tactical compromises that German fighters exploited mercilessly. Morrison's testimony crystallized Whitmore's resolve to succeed, regardless of official disapproval or career consequences. By early September, Whitmore's unauthorized research had attracted unwanted attention from his superiors, who discovered evidence of his experimental work during a routine laboratory inspection. Wing Commander Harold Fitzpatrick, the senior administrator overseeing fuel research operations, summoned Whitmore to a formal disciplinary meeting and delivered an unambiguous ultimatum: cease all unauthorized experimentation immediately, or face court-martial proceedings for insubordination and misuse of government resources. Fitzpatrick represented the institutional mindset that prioritized procedure over innovation, viewing Whitmore's independent research as dangerous precedent that could undermine military discipline and established procurement systems. The meeting revealed fundamental philosophical differences about research methodology and military priorities, with Fitzpatrick arguing that proper channels existed for fuel development, while Whitmore countered that urgent battlefield needs justified exceptional measures. Whitmore attempted to present his preliminary findings demonstrating significant octane improvements through specific chemical additives, but Fitzpatrick dismissed the work as uncontrolled experimentation that could never meet military specifications. The confrontation escalated when Whitmore produced combat reports documenting British performance deficits and argued that institutional inertia was literally killing RAF pilots. Fitzpatrick responded by threatening immediate transfer to a non-research position if Whitmore continued pursuing unauthorized projects, effectively ending his career in fuel development. The ultimatum forced Whitmore into an impossible choice between career preservation and moral conviction, between following orders and potentially saving lives. He requested 48 hours to consider his position, knowing that he had already decided to continue his research regardless of consequences. That evening, he received word that James Morrison had been shot down over Kent, his Spitfire reportedly unable to climb quickly enough to escape attacking Messerschmitts. The personal loss transformed Whitmore's technical challenge into a moral crusade that transcended career considerations and military protocols. He spent the night calculating exact chemical ratios for his most promising fuel additive, knowing that success might vindicate his methods, while failure would certainly end his military service in disgrace. The next morning brought another conversation with Fitzpatrick, who noticed Whitmore's obvious exhaustion and pressed him for a final decision regarding future research activities. Whitmore looked his superior in the eye and lied, promising to abandon experimental work while secretly planning the most audacious violation of military procedures in his career. September 15th marked the culmination of Whitmore's months of unauthorized research and the beginning of the most consequential 48 hours in aviation fuel history. Working alone in his laboratory after normal duty hours, he carefully measured precise quantities of tetraethyl lead, aromatic hydrocarbons, and proprietary chemical compounds that existing regulations classified as too hazardous for aviation use. His experimental fuel additive required exact molecular proportions that he had calculated through theoretical chemistry and refined through dozens of small-scale tests, creating a mixture that could theoretically boost octane ratings from 87 to over 100. The work demanded extraordinary precision because slight variations in chemical ratios could produce explosive instability rather than enhanced performance, turning aircraft fuel tanks into airborne bombs that would incinerate pilots rather than power their engines. Each measurement required steady hands and absolute concentration, qualities that proved challenging after weeks of secret research and mounting official pressure to abandon his experiments. The laboratory environment itself presented additional dangers, with chemical vapors that could cause unconsciousness or respiratory damage if ventilation systems failed to operate properly. Whitmore wore improvised protective equipment and worked with windows open despite blackout regulations, accepting the risk of air raid exposure rather than chemical poisoning. His theoretical calculations indicated that successful fuel enhancement required adding his experimental compounds to standard aviation gasoline in precise ratios, creating a hybrid mixture that preserved existing supply chains while dramatically improving engine performance. The critical test would involve running actual aircraft engines on his experimental fuel under conditions that simulated high-altitude combat stress, measuring power output and operational stability across varying throttle settings and atmospheric pressures. However, conducting such tests required access to aircraft engines and official authorization that his superiors had explicitly denied. Whitmore solved this problem through careful relationship building with maintenance crews and test pilots who shared his frustration with current fuel limitations and trusted his technical expertise despite official disapproval. Sergeant William Hayes, a veteran engine mechanic with 30 years of Royal Air Force experience, agreed to participate in unauthorized engine tests scheduled for the following evening, when fewer personnel would witness their activities. Hayes possessed intimate knowledge of Merlin engine specifications and operational parameters that would be essential for interpreting test results and ensuring pilot safety during any eventual flight trials. The unauthorized engine tests on September 16th revealed results that exceeded even Whitmore's optimistic projections, demonstrating performance improvements that could fundamentally alter the tactical balance of aerial warfare. Working in a secluded hangar at Farnborough with minimal lighting to avoid detection, Whitmore and Sergeant Hayes installed his experimental fuel in a Rolls-Royce Merlin engine identical to those powering Spitfire and Hurricane fighters across British airfields. The initial engine startup proceeded normally, with standard ignition sequences and warm-up procedures showing no unusual characteristics or performance anomalies. However, as Hayes gradually increased throttle settings, the engine began producing power outputs that dramatically exceeded manufacturer specifications, delivering nearly 20% more horsepower than the same engine had achieved using standard aviation fuel. The sound alone told the story. Instead of the familiar roar of a Merlin engine at maximum power, they heard a deeper, more resonant tone that suggested reserves of energy waiting to be unleashed. Measurement instruments confirmed what their ears detected, showing sustained power levels that existing fuel formulations could never maintain without catastrophic engine damage. More importantly, the experimental fuel maintained stable performance across the full range of simulated altitude conditions, delivering consistent power output at atmospheric pressures equivalent to 35,000 feet above sea level. Standard fuel typically suffered significant power degradation at such altitudes, forcing pilots to accept reduced climb rates and maximum speeds that German fighters exploited ruthlessly. Hayes monitored engine temperature, oil pressure, and combustion characteristics throughout the extended test session, finding no evidence of the instability or mechanical stress that fuel development textbooks predicted would result from such dramatic octane enhancement. Instead, the engine ran smoother and cooler than normal, suggesting that Whitmore's chemical additives actually improved combustion efficiency rather than merely increasing raw power output. The implications became clear as they completed successive test runs. Aircraft equipped with this experimental fuel could climb faster, fly higher, and maintain superior performance at altitudes where current fuel formulations failed completely. Hayes, whose mechanical experience spanned decades of engine development, declared it the most significant advancement in aviation technology he had witnessed since the introduction of the Merlin engine itself. However, transforming successful laboratory results into operational reality would require convincing skeptical superiors and overcoming institutional resistance that viewed unauthorized innovation as dangerous precedent. The critical moment arrived on September 17th when Whitmore faced the choice between continued secrecy and open confrontation with military authority. Wing Commander Fitzpatrick had scheduled another inspection of fuel research activities, intending to verify that unauthorized experimentation had ceased as ordered. Whitmore possessed documented evidence of his experimental fuel's revolutionary performance, but presenting that evidence would constitute direct admission of insubordination and deliberate violation of explicit military orders. The moral calculus seemed straightforward: reveal his breakthrough and face court-martial proceedings, or maintain secrecy while British pilots continued dying from fuel-related performance deficits. However, the tactical situation had grown more desperate during the previous week, with RAF Fighter Command reporting unsustainable loss rates and growing German pressure that threatened Britain's air defense capabilities. Intelligence reports suggested that Germany was planning massive daylight bombing raids against London and other strategic targets, attacks that would succeed if British fighters could not achieve tactical parity with Luftwaffe aircraft. Whitmore realized that conventional bureaucratic processes would require months to evaluate and implement his fuel improvements, time that Britain simply did not possess. The decision crystallized when he received word that 3 more pilots from local squadrons had been shot down during the previous day's fighting, bringing the total casualties among his personal acquaintances to 7 experienced aviators whose deaths might have been prevented by superior aircraft performance. He prepared a comprehensive technical presentation documenting his experimental results, including detailed chemical analysis, engine performance data, and tactical implications for aerial combat operations. The presentation required careful balance between scientific objectivity and emotional urgency, demonstrating technical competence while conveying the life and death implications of continued delay. He scheduled individual meetings with key personnel who possessed authority to approve emergency fuel procurement changes, including Group Captain Robert Stanford Tuck, the senior operations officer responsible for fighter squadron performance. Stanford Tuck had earned legendary status as a combat pilot before transitioning to administrative duties, giving him credibility with both technical personnel and operational commanders. More importantly, Stanford Tuck had publicly criticized institutional obstacles that prevented rapid implementation of battlefield innovations, suggesting receptiveness to unconventional solutions that offered tactical advantages. Whitmore's strategy involved presenting his experimental results as accomplished fact rather than theoretical possibility, demonstrating that high-octane fuel enhancement was immediately achievable rather than future aspiration requiring extended development. Group Captain Stanford Tuck's reaction to Whitmore's presentation exceeded the most optimistic expectations, transforming potential court-martial proceedings into emergency implementation planning. The veteran pilot immediately grasped the tactical implications of 20% power improvement and consistent high-altitude performance, recognizing that such capabilities could fundamentally alter the strategic balance of the Battle of Britain. Stanford Tuck had personally experienced the frustration of fighting German aircraft that possessed superior climb rates and ceiling capabilities, understanding from direct combat experience how fuel limitations translated into dead pilots and lost battles. His response was immediate and decisive: authorize emergency production of Whitmore's experimental fuel for combat evaluation, beginning with volunteer test pilots from his most experienced squadrons. The authorization required Stanford Tuck to assume personal responsibility for any negative consequences while bypassing normal procurement procedures and safety evaluations. However, his combat experience convinced him that the potential benefits far outweighed regulatory risks, particularly given the desperate tactical situation facing RAF Fighter Command. Within hours, Stanford Tuck had assembled an emergency meeting including senior technical officers, squadron commanders, and logistics personnel capable of organizing rapid fuel production and distribution. The meeting revealed both institutional support and resistance, with traditional administrators expressing concern about safety protocols, while operational commanders demanded immediate implementation regardless of bureaucratic obstacles. Wing Commander Fitzpatrick attended the meeting and attempted to reassert his authority over fuel research operations, arguing that unauthorized experimentation violated military discipline and established safety procedures. The confrontation between Fitzpatrick and Stanford Tuck represented broader philosophical differences about innovation, risk assessment, and military priorities during wartime emergencies. Stanford Tuck ultimately resolved the dispute by invoking emergency operational authority, declaring that combat necessity justified exceptional measures that peacetime regulations could never anticipate. The decision effectively ended Fitzpatrick's opposition while placing Stanford Tuck's career at risk if Whitmore's experimental fuel produced catastrophic results. Production planning began immediately, with chemical procurement specialists calculating raw material requirements and manufacturing personnel identifying facilities capable of producing Whitmore's fuel additives at operational scale. The first combat trials of Whitmore's experimental fuel took place on September 20th, with volunteer pilots from 611 Squadron conducting high-altitude interception missions against incoming German formations. Squadron leader David Bennett, an experienced pilot with 12 confirmed victories, flew the initial test mission using aircraft equipped with the enhanced fuel formulation. His Spitfire achieved climb rates and operational ceilings that exceeded any previous performance, reaching 32,000 feet in under 8 minutes compared to the normal 12-minute requirement. The improvement allowed Bennett to intercept German formations before they reached optimal bombing altitude, engaging Luftwaffe fighters under conditions that favored British tactical advantages rather than German superior performance. Radio communications from the test flight revealed Bennett's amazement at his aircraft's enhanced capabilities, reporting sustained high-altitude combat maneuvers that would have been impossible using standard fuel. More significantly, Bennett successfully engaged and destroyed 2 Messerschmitt fighters during combat that would previously have ended with German escape through superior climb performance. His post-mission debrief documented specific tactical advantages: faster acceleration, higher operational ceiling, improved turning radius at altitude, and sustained power output during extended combat engagements. The success prompted immediate expansion of the test program, with additional volunteer pilots requesting access to the experimental fuel despite potential safety risks and unknown long-term effects. Squadron commanders reported dramatic improvements in pilot confidence and tactical effectiveness, with aviators expressing enthusiasm for combat missions rather than resignation to technological disadvantage. Within 72 hours, word of the experimental fuel's performance had spread throughout RAF Fighter Command, creating unprecedented demand for wider implementation despite continued official reservations about safety and procurement protocols. Technical analysis of aircraft engines after combat flights showed no evidence of mechanical stress or operational degradation, confirming Whitmore's theoretical predictions about improved combustion efficiency and engine preservation. The tactical implications became clear as German intelligence reports began noting unexpectedly aggressive British fighter performance and higher altitude interceptions that disrupted Luftwaffe bombing formations. German commanders attributed the change to improved pilot training and tactical modifications rather than technological advancement, failing to recognize that fuel enhancement had fundamentally altered the strategic balance of aerial warfare. October brought official recognition of Whitmore's contribution and emergency authorization for full-scale production of his high-octane fuel additive. The Air Ministry, faced with irrefutable evidence of tactical superiority and mounting pressure from operational commanders, formally approved immediate implementation across all RAF fighter squadrons. The decision required overriding established procurement procedures and accepting chemical formulations that traditional safety evaluations had not fully tested. But combat results provided compelling justification for regulatory flexibility during wartime emergencies. Wing Commander Fitzpatrick found himself reassigned to administrative duties remote from fuel research operations, his opposition to innovation having been thoroughly discredited by battlefield success. Whitmore received promotion to squadron leader and appointment as Chief of Fuel Development for RAF Technical Services, positions that provided authority and resources to continue advancing aviation fuel technology. More importantly, his experimental additive received official designation as Fuel Mixture No. 105, acknowledging its octane rating and establishing standardized production specifications for manufacturing facilities throughout Britain. Chemical companies that had previously dismissed his theories as impractical began requesting technical consultations and licensing agreements, recognizing commercial potential in fuel enhancement technology. The production scale required careful coordination between multiple manufacturing facilities and transportation networks, creating logistical challenges that tested Britain's industrial capacity during wartime resource constraints. However, the tactical advantages justified extraordinary measures, with fuel production receiving priority allocation of chemical components and manufacturing equipment normally reserved for munitions production. By November, virtually all RAF fighter aircraft operated using Whitmore's enhanced fuel formulation, creating consistent tactical superiority that German commanders found increasingly difficult to counter. Luftwaffe intelligence reports began documenting unexplained British aircraft performance improvements, leading to German efforts to develop comparable fuel enhancement technology. The strategic impact extended beyond individual combat engagements, affecting broader campaign planning and resource allocation as German forces recognized their aerial advantage had been neutralized through technological innovation rather than numerical superiority. Combat statistics from late 1940 showed dramatic improvements in RAF performance, with loss rates declining significantly while victory totals increased across all operational theaters. Post-war analysis would reveal that Whitmore's fuel development contributed to saving an estimated 15,000 Allied air crews and shortening the European conflict by approximately 8 months through enhanced tactical capabilities. His innovation influenced subsequent aviation fuel development throughout the post-war period, establishing chemical enhancement principles that remained standard practice for military and civilian aircraft operations. The Royal Aircraft Establishment institutionalized his research methodology, creating formal programs for rapid innovation and battlefield implementation that balanced safety considerations with tactical urgency. Universities began studying his work as a case example of how individual technical expertise could overcome institutional resistance and bureaucratic inertia during crisis situations. His personal story became legendary within aviation engineering circles, inspiring future generations of researchers to challenge conventional wisdom when circumstances demanded innovative solutions. Letters from surviving pilots and their families documented the human impact of his contribution, describing how fuel enhancement technology provided tactical advantages that saved lives and enabled mission success. James Morrison, whose death had motivated much of Whitmore's determination, was posthumously honored through a memorial fund that supported aviation research and pilot training programs. Whitmore himself remained characteristically modest about his achievements, emphasizing teamwork and institutional support rather than individual brilliance when interviewed about his wartime service. He returned to civilian life after the war, working as a chemical consultant for petroleum companies while maintaining informal advisory relationships with military fuel research programs. His marriage to Eleanor Patterson in 1946 produced 2 children who followed careers in engineering and chemistry. Continuing family traditions of technical innovation and practical problem-solving, professional recognition included election to the Royal Society of Chemistry and numerous industry awards acknowledging his contribution to aviation fuel development. However, Whitmore valued most highly the personal letters from pilots and their families, tangible evidence that his technical work had preserved human lives and contributed to ultimate Allied victory. The octane enhancement principles he developed remained classified for several years after the war, but eventual declassification allowed broader application in civilian aviation and automotive industries. The broader historical significance of one man's determination to challenge authority and pursue technical excellence demonstrates how individual courage can overcome institutional obstacles and change the course of human events. Thomas Whitmore's story illustrates the complex relationship between military discipline and innovative thinking, showing how rigid adherence to established procedures can become counterproductive when circumstances demand rapid adaptation and creative solutions. His willingness to risk career and reputation for the sake of technical advancement exemplifies the moral courage required for breakthrough innovation during crisis periods. The fuel enhancement technology that emerged from his unauthorized research influenced not only immediate tactical situations, but also long-term strategic capabilities that shaped post-war aviation development. His experience reveals how bureaucratic resistance to change can inadvertently perpetuate technological disadvantages that cost lives and compromise military effectiveness. The ultimate vindication of his methods through combat success established precedents for emergency innovation programs that balanced regulatory compliance with tactical necessity. Future military research organizations would study his approach as a model for rapid technology development during wartime conditions, recognizing that conventional procurement procedures often proved inadequate for urgent battlefield requirements. The chemical principles underlying his fuel additives continued evolving throughout the jet age, contributing to propulsion systems that enabled supersonic flight and space exploration. His personal transformation from obscure laboratory researcher to recognized technical authority demonstrates how crisis situations can reveal exceptional capabilities in seemingly ordinary individuals. The moral dimension of his choice to disobey orders for the greater good raises fundamental questions about individual responsibility and institutional authority that remain relevant for contemporary military and civilian organizations. Would you have possessed the technical confidence and moral conviction to challenge established authority when lives hung in the balance, risking personal consequences for the sake of technological advancement that could benefit countless others? Comment below and share the story, so others remember that sometimes the greatest courage comes not from following orders, but from having the wisdom and determination to break them when human lives depend on innovation over compliance.